Good morning. So we've been cruising along this week on the kind of metallurgy and plastic science and engineering. The reason I go through these details is the same way that casting gets you to start making products, and then you deform it. In the end, if you're looking at a special application, the heat treatment comes in, and I have to say it's a good day today, and it's a good time to start talking about joining, because I mentioned it at the beginning of the class that it's one very important aspect. It's how we can be effective in making complex assemblies in small quantity, and understanding welding, for example, helps you in any sort of design or analysis, engineering analysis of a structure. So I've put up the lecture notes, and I think I even included tomorrow. So it's a little bit ahead now. So tomorrow the focus is really going to be on fusion welding. Today is a little bit of a transition, wrapping up the heat treatment. We'll talk a little bit about surface modification, and we'll talk a little bit more about the surface, the term project. There are a few things that I wanted to reach out to you for today. So again, just a transition lecture, and we'll, as usual, welcome questions. Please interrupt me. I get bored. So let's get started. If I put it there, is that going to work? Yep. We talked last time about how you take aluminum and make it stronger by forming these precipitates. I won't go back to all that we discussed, but maybe I'll point out this scale here is 0.5 micrometer for these precipitates. So it was done using a transmission electron microscope. That's how you find out what you have. And we talked about the precipitates being much smaller at the low temperature. And one thing I may not have emphasized enough is these intermediate precipitates that give you the highest strength, because they are obstacles that are still part of the grains, so they impede the movement of dislocations. And they're bigger than these very, very small ones that are there on the screen. We talked about the process for aluminum to put it in solution. So that's heating it up, so it's all part of the same crystal structure. When you quench, you freeze that structure. If you recall, we talked about the aircraft fuselage that was being stretch formed over these dies to make the complex curvature. So that process helps with initiating the precipitates, because you essentially have a lot of dislocation movement in the structure. So it's a way to help get a better aging when you deform the material first. There are a few examples like rivets for aircrafts that do not need to be heated to age. So what happens is they take they're a little bit like studs. So we're not talking about pop rivets. We're talking about the real solid rivets. So they look a little bit like this. You have the shaft, and then you have your head, and it's very solid. So you make that piece, you have a bunch of them, you put them in a screen, heat them up, quench it. Then what they do is they put it in a freezer, and they have a maximum of time they can keep it there. Let's say for 4 days it can be in the freezer. And when somebody needs it to feed it into the machine, they use a lot of machines to make those. What happens is, let's say now that it's making that lap joint, and it becomes, let's say it's just mushrooming like this. So it's making the lap joint. You have two thicknesses in there. That deformation, well, first of all, you bring it back to ambient temperature, then you deform it. Those two processes gets you this ambient temperature aging, where you're forming the precipitates and you increase your strength. There's a lot of parameters on this part that's going to influence the hardening behavior. It's not just the chemistry, it's the microstructure, and then it's how much you deform it. So the only reason I know about this is I was actually doing the little hardness test to make sure from 1 week to the other that we were always getting the same effect on the rivet. And we would do complete destructive pull test on a subset from each assembly. And there was a tracking system where we knew which batch went where. So by the time you do the pull test, a lot of times the rivets were already in the machine. But if you had a problem, you can go back and take those rivets out and start over again. Didn't happen very often, but the system is essentially pretty secure, so you don't have a change in your process parameter that will not give you the characteristics you were looking for. So from very, very simple, we talked about using the aluminum alloys that are already heat treated where you just machine it. I gave the example of a 6000 series aluminum. That one, there's just the heat treatment is already come into the bar that you're using. And these other example that we just talked about is completely opposite. No way. I broke it, I think. All right, it's back. Okay. So for steel, that was a slightly different story. I said that you have this diffusion-less transformation when you cool it off. And when you have diffusion, those lamellar, I don't think I had a good image of it yesterday, but here you can see the dark zone that are carbon-rich, and the white zone are the grains that are just the iron, and that's typical for low-carbon steel. And then you have other grains that have a mixture of the very hard and the soft face. So that is the type of microstructure that gives you the 30 KSI or 200 megapascal yield strength. And this one here, where it's quenched, it has more of the needle or the plate-like feature from the martensitic transformation. So it's looking very different. First of all, you only really see one face here. And that structure needs to be tempered. So you have a good combination of strength and ductility. Okay, so what we're going to do, give you some example of what we use heat-treated steel. We've alluded to some of those on the board, but I have a few images for that. And then we'll talk about surface modification. I've got some examples here. Oh, I brought an actual, because last time I brought a fracture specimen. This one is just a straight, we call them a duck bone. So it's a tensile specimen. It's a strip that has a little machine section, and it was taken out of a tubing, oil and gas tubing. So it's round, and that's how you keep it typically. So you just cut around the circumference. It still has this curvature, and where you grip it at the end, it becomes flat. Not the most sophisticated test, but it does the trick. This one is about 100 KSI yield. So you can see it didn't deform that much. It almost looked like a brittle type behavior on the fracture surface. And it was corroded on the inside. This was a service piece. So the test doesn't really meet the ASTM standard requirement, but it's what they decided to do. And then I'll start talking about welding. So we talked about using high-strength steel in concrete, and one argument was there's only so much room you have to put the reinforcement if you're still going to say you have enough concrete to isolate the steel from the environment. The whole idea here of reinforced concrete well, there are many ideas. There's cost, but in terms of longevity, you're relying on the stability of the concrete to keep the steel at high pH so it doesn't corrode. So we do this here. I've talked about making this inner layer, so they call it the concrete core, wrapping around the pre-stressed wire. There's actually extra level of detail here, and you can also see they have this little end piece that gives a little extra strength because you need to connect these together. It's very nice to think I'm going to make this really wonderful cylinder, but you have to connect it together, and that brings me to this same concept. If I want to make a pressure vessel, I have to think that there's going to be some end pieces to it. It's a full enclosure, so I can't just use a pipe without having a form of joining in the end. So joining really becomes important, and maybe this is one of the place where, for big application, 3-4 years ago, we had a big leak on the MWRA, so the old Massachusetts Water Resource Authority, that caused everybody having to boil their water for 3 or 4 days, except for Cambridge. Cambridge has its own water source. So that what happened was not those big pipes themselves, but the joint between them. The joints are made out in the field, and you do try to have some allowance for alignment and a number of characteristics, but it is essentially vulnerable to exactly how it was installed. In this specific case, they ran out of bolts, so somebody went out and bought some extra bolts that were not necessarily to specification. And of course, it's always after the fact that you realize, oh, maybe it matters. Maybe this was not a good idea. So this is another situation I've been involved with, and it relates to when we talked about fracture surfaces last time and the time before. It's a hardness clamp. So if you have two pipes that have a little lip, so two big cylinder, one has a little reinforcements on the outside, it looks like this. You have the other one that also has the lip, and then you come with a clamp on top, pretty much like this, and that goes around the circumference. So they call it a hardness clamp, and I drew it correctly in the sense that you don't need too much precision. You can have a little gap there, but it has the purpose of making sure that the pipes don't completely disconnect from each other. In this specific case, you could see that it cracked right in the corner over here. That was a new project in Chicago, and they were doing the pressure testing when it came apart. And the main finding from looking at the fracture surface was there was one initiation site, so one spot that didn't work the way it was supposed to. And what happened is when they tried to engage these things, there was one spot where either there was a debris or the pieces were a little too far apart, so it didn't get all the way in. So we could see the bearing mark kind of halfway here on this component, and so there was a lot more bending in that corner than there would have been if the clamp was put on properly. Now, when we looked at it, the clamp was completely off, broken, and it would have been hard to look for this mark over 30 feet of diameter. It's just not practical. The shop was pretty dark. So it's really by looking at the fracture surface and knowing where it started to crack here on the 30 feet that we just had the cylinder turn. And I looked closely here to see if there was anything I could find, and that's where I saw it. It was lifted. So just an example of, in 48 hours, they knew that the steel was not the problem. They could remake that joint the same way, but they had to tell the field guy not to try to take shortcuts. Okay, these may not look impressive here, but the equipment for drilling and offshore operation is very sophisticated. I mean, you have to think, let's say you're drilling a hole that is 20,000 feet, so 4 miles below the ocean floor, and it's going down straight, then it turns, and they have all sorts of conditions they encounter. So they are asking for very resistant material to wear, good mechanical properties. They only make the hole so big, and they need that string for 4 miles to be carrying the torque to continue drilling and pushing. So those materials are in the 100 KSI type range. They went through a heat treatment. The welding of them is very important. So in this case here, it's a little bit of a friction welding that they have been using, where you able to do it quickly and you don't change as much the microstructure. You know, you still have to do a heat treatment after the fact. So the only way to make this equipment is to fully assemble it and then do a final heat treatment to get the best mechanical properties. There's a student last year that worked for BP in the offshore oil and gas division, and that's the only thing she did for 4 months, was to help with the development of the process specification for this type of welding, for a very specific type of pipe that had to be able to deform. See, if you have a very, very long string from the barge on the ocean down to the seabed, this last piece close to the bottom of the ocean sometimes needs to be able to deform and actually change shape. And you don't put just a hinge there because you need to be carrying the fluid. So they were working on special titanium alloy just for their fatigue resistance, so their ability to deform repeatedly. It was a very interesting project, very technical to some extent, so she had to brush up on some of the things we've talked about for the past 3 lectures on grain size, metallurgy, heat treatment, welding, but she liked it. There are other types of joints. So this one here, when you make the tread, one piece come into the other, and that's used a lot for drilling. These are the very demanding application. Let's say we take a step down, and all we're trying to do is to install a pipe in the hole for production. So you lower it there, and it's going to be used permanently. So those pipes, what you see is there's essentially a coupling to connect them together, and you have a little extra material. There's no need to weld. That's the biggest advantage from a manufacturing standpoint. This is less expensive to make because you make the pipe, you machine the ends, and then you make some couplers, and that's the end of it. You don't have to come and have this change in section, because when the joint is included here, you see that it's much bigger over the joint than it is on the base material. There's another thing to note is this region of the weld, it has a bigger cross-section than the plain pipe itself. So that's a practical way where they make sure that they don't have the highest stresses. Okay, so now we're into completely new material. It's important to think about high-strength steel, let's say for a wear application, so gears and bearings and things that the surface hardness, and when I brought the axle of the railroad, I didn't bring it back again today, but you have a surface treatment because you don't want that component to wear on the surface, and then you don't want the entire section to be that hard because it's going to be brittle. So you make your surface essentially resistance to wear and crack initiation, and then you make the center of the piece very resistant to the growth of these cracks. So if you start a crack, a lot of times it will stop when it ends, it come out of this hardened zone. Now, how do we do this? You want the surface to be very hard, and then you want your core to be softer. There are multiple ways, and maybe we'll list them. Well, this very first one is adding carbon to the surface. So you do carburization. It's a diffusion process. You just put the metal on the oven, and then you put a carbon-rich atmosphere for a few hours, depending on how deep you want to be. The pieces I have here, and we're not talking about things that are super sophisticated, just these kinds of fasteners that can be used on buildings. Not this one. I didn't bring the self-drilling one. There are some fasteners you have that you'll, it has a little bit of a drill bit in the end, and then it has a threaded portion. So you drill the hole, and then you're able to put the bolt in it right after the fact. So it saves a lot of installation time. But the idea is that's a good example of wanting a very hard surface, and you still want the core to be able to deform. So if there's an overload, you don't want the fastener to crack in a brittle way, just like this one. Snap. That's not good. So the surface here, you can see, is a little darker. It looks like a tempered martensite. And then the center in this case was still pretty hard. So this was fairly high strength steel altogether, but the surface in particular and all those threads were much harder. So the reason for doing this, again, it could be wear resistant, it could be fatigue resistant. In this case, the ability to be able to drill into some other steel that's softer, and then still be able to deform and not break in a brittle manner, so have some toughness in the core. What else can you do if all you're looking for is improving your wear resistance or your fatigue resistance? So for fatigue, there's a process that's called, and you can do it with nitrogen here. So there's a nitration and a carbonitration. These are all diffusion processes. So I'll just say, nitrogen as well, or a combination of both. The whole idea is to reinforce the surface. Now, if we talk about something that's very different, you have all sorts of treatment to deform the surface, and a shot peening is a very general term for that. So what happens here is you have balls of different sizes, and they do that for aircraft, for the main structure, and then so you shoot balls on the surface, it deforms it and create this layer that has been hardened, so cold form. And not only it increases the yield, but it gets you a compressive layer. So why is that? So let's say I have the surface here, and I come and I compress the surface. So I'm forcing this surface to become a little narrower in thickness. So what that means is the surface is trying to expand sideways. It's getting squished and it's trying to expand, but it is constrained. Each little ball, when it hits, can't really grow the plate. So the plate stays the same size and the surface just becomes in compression. So there's a net small reduction in thickness, and there's this compressive stress field in plane. So it's an effective way. It's used for helicopter blades and a lot of aircraft components. Some of the drilling equipment goes through this process as well. And depending on the size of the bead, you can specify a certain depth to this deformation layer. So it's, in this case, it's really a mechanical way to work the surface so it's in compression. I believe Professor Eager in his module talked about tempered glass. So this, in that case, is through the heat treatment that you get the surface compression. And you may come up, if you think about it, you may come up with other ways that we could do this, that just benefit from surface modification to enhance the overall performance of the part. Because these are, well, shot peening does come to a cost. The carburization is not super expensive if you're planning to do a heat treatment anyway. It does change the appearance of the part, so sometimes that may matter. A lot of time doesn't. So we'll start about welding, and I want to introduce you to somebody I don't know. The basic process of arc welding has been around now for a while, and it's very powerful because it's quick. So if I take two parts, you almost need to try it to see, and they don't line up perfectly. There's a little bit of a gap. It's okay because you're going to come and melt a little bit of each part, and it solidifies quickly, and then all of a sudden you have a continuity in your materials. So let's say it's on a thick plate. I come with one side, and let's say the other one for my makeup, because a lot of times when you're trying to weld assemblies, even in shops, you take all the pieces and you put them together in a certain shape. Then you start welding and adjusting. So you don't need these cuts to be absolutely precise. Actually, a lot of times you want a little gap between the pieces. So you're able to take these parts, put them together. Let's say you hold this here, you hold this there, and after the starting to tack weld, we call, so you put a little weld here and there, you can verify that overall your dimensions are correct. If not, you use a hammer and move things around, you use a press, and when you're happy with it, then you go in and complete the welding. So that's when I talked about the example of the radio telescope yesterday. That's what they did. They had the entire assembly made with just small welds. Something goes wrong. Let's say I put a little weld here. You just grind it off. Move things around until you're happy with everything that you have in terms of geometry. So if somebody says, well, I would rather use bolts, for example. Well, with bolts, you do have to drill in the two components. First of all, you can't really make a butt joint like this. You need a lap joint. You could put a strap. So the alternative here is, let's say I have a strap, and it's put a hole, and I weld it. So I bolt it here, bolt it there. So I don't need to have that weld. So we have to align this with this and this with that. So the only way that it's done on large structures is you do the hole in the field. Or you have the hole just on one side and you do the hole on the other side. But I hope you see it's just very difficult. And then when you tighten everything up, does it guarantee you that it's not going to move? Well, not really. You know, it can start sliding and move relative to the other. So in terms of ease of access, ease of putting different parts together, the welding is very, very effective. And cars, we talked about most big structures, you have some welding in them. And we talked about the effect on strength. But before that, if you go to a shop and you see this blue flame, that is damaging to the eye. So it's in the spectrum that you want to not look at for a long time. Now, it's not like instantaneous. It's just something to know. It looks cool, but you don't want to be looking at it. The other aspect, when it's red, that's just cool. You know, you don't want to be close enough, so you get heat. So when somebody is cutting something, that is not damaging to the eye. Okay, we'll talk a little bit more about what happens when you take, with enough training, a welding machine, and you come with an electrode and you arc against the surface. So there are a couple of things you do need to do is you put the ground on the part. That's how you get the current to go through and create the arc. The arc is going to melt both the base material and your welded electrodes. We're just talking about the very, very basic welding process, and I'll expand to what happens into other situations. So, melted steel, whoa, it will want to oxidize. So what it means is in this case, and there are other cases we'll go over, it's a very important part of welding to protect that melted steel so it doesn't oxidize and become extremely brittle. So in this case here, it's essentially a little bit of a slurry that is over the metal electrode, and those shielded electrodes need to be kept dry a lot of times if it's a good quality electrode, so you don't have the moisture starting to come in when it engages with the liquid steel. So let's say it has been kept dry. What happens is it also melts and becomes a slag. And what a slag does with respect to the steels, first of all, it really is a blanket. So now the liquid steel doesn't see directly the oxygen from the atmosphere. But the other aspect, it has a cleaning power. So you have liquid steel in contact with essentially a floating slurry on top, and there is a thermodynamic force for that. That slurry is designed so it will grab on impurities. So let's say the steel you use on the first place was not completely clean. So I start here. This is my plate. Turns out it was a piece of a bridge or anything. It came out of another guy's shop. It had some oil on it. Clean it a little bit, maybe, but it's typically not done perfectly. It's going to have a mill scale. So you go and start arcing against it. So you melt a little bit of that surface, and you melt the electrode. And really what happens is contaminants do have the time, because it's so high temperature that diffusion is strong, they have the time to get to that slurry. So one implication of that is when you don't really have a clean surface or a clean steel composition, it's very advantageous to have a welding process just like this one that has a slag, because it will clean up. There are other processes that we'll go over that don't have this, and they do require more cleaning beforehand. So it's more forgiving here. It's the traditional way, and we'll go over what can happen and not happen. But so the aspect of melting the steel and protecting the environment to some extent, if you do it right, it's all good. And a lot of times there's going to be a little bit more money spent in the metal that you bring in to weld than the big piece that you're welding. So you're able to make this weld metal a relatively good quality. And a lot of time you end up worrying about what you did to that base material more than anything else, because you come and you heat up this zone, and then when the arc goes away, it cools very, very quickly. So you went through a heat treatment, and that leads to residual stresses the same way that you do with tempered glass. The main difference is the center of your bead typically has some form of a tension component one way or the other, because it's the one that was the hottest and that cooled down the most, so it's going to typically be in tension. Residual stresses and heat treatment, of course you have some geometry sometimes. It's going to look a little more rough, but I think in general it's less of an effect than what you did to the different metals through this process, and then the residual stresses that you end up with. we're still in the very introduction, and what I do tomorrow, I have plenty of examples of things that work and doesn't work. But perhaps now, again, on the basic level is the goal is to melt both metals. Does it happen all the time? The answer is no. So we're looking here, and we'll go over the application of that next time, but just for the base principle, we're looking at a bar, a round bar, that is being welded to a plate. So what happens is just a very small section like this of a bar that then goes and bends, and it's going onto this flat surface here of another structure. So it's kind of a special case where one surface is flat, the other is curved, and you try to weld between them. Not ideal, but what happens is these bars are effective in terms of weight, so, and therefore, if you're able to weld them good enough, you do. So it's a difficulty because of the access to weld between those two surfaces, but you'll see a lot of times the structures for roofs on building, and this one was in a big greenhouse, a 25-acre tomato greenhouse. What happens is you can align your torch. So there are two things that happen. This material here, the flat piece, is thinner. It doesn't show there because we cut the bottom, but it's much thinner than this bigger piece. So what happens then is when you come with the heat, you need to heat a little bit more the thicker component. That's a necessity. And then the question is, are you going to be arcing only with a bigger component, or are you going to be arcing with both? And you see both cases. So in the low fusion case, the welder came and pretty much had the torch going straight to the round bar, and you don't have much penetration. So the weld pool only, here there's actually a gap. And then over here, there's a little bit of a fusion. So maybe the fusion is about from here to here, let's just say, for example. Whereas in the other case, you can see that fusion line on both sides, and there's been a good connection. So it may look like an unusual case, but what happens in this project is they didn't do a good job in the first place. Now, it was done overseas, which it's just part of the reason. The main reason, it's a difficult geometry, because when the customer asked them to redo the work, you could tell that they took a very, very special care, and they still had issues like this. So this was a quality assurance verification on the replacement one, the better one. The other one really had almost 25–30% of the joints that were not fused. So I mean, from a general engineering standpoint, what it means is it is a cost of trying to go quickly, make things that are very complex to do. You have more risk of not having it perfectly. And it is still the case with a lot of structures that you'll have little rivets, little joints, all sorts of things going on. But when it comes to really the primary joints, you'll still have a bolt, or you'll have something that a lot of times is, first of all, you can remove it, like the wing of an aircraft holds with 12 bolts, that's it. But at the same time, you know exactly how they put in, and if you need to take the wing out, you just take it out, put a new one in. So it's just, I guess, the counter side of being able to do it very quick here, and without a perfect alignment of everything. So even if your bar doesn't fit perfectly, you move it a little bit, you just go. And at the speeds, these machines, when they all set up, it's a semi-automatic welding. So they really come and do it just about like that. It's very quick. And there's more time spent after the fact in complaining about, what was good and not good. So we'll go over that detail of how you can make joists by welding without getting into these types of problems. There's a lot of other details you can use. But I do want to emphasize a few things that, I think we talked enough about the flux, the oxidation. There is a solidification. So the center of your weld metal, the good news, it's solidified very quickly. So it has a very fine structure. It doesn't have these big dendrites that we talked about when you have the big castings. But it is a casting. So in terms of toughness and ductility, you have to spend more on the alloying so you can do it correctly. The heat treatment, in the case of the drill string, I mentioned you try to do all your welding first, and then you send it for heat treatment. And I have a big example of that. I don't know. We're not going to do it right now. I say it's a reduction in the fabrication cost in most cases when you can do it. Sometimes it will lead to a risk of preferential corrosion, especially on stainless steel. If your composition of the two metals are not the same, you can have a little bit of a galvanic effect with the weld metal. It's not super common. A lot of times you try to protect the structure. If you galvanize it, you're okay. So it's a little bit of a combination of everything that we've talked about since the beginning of the class. You cast, in this case, you don't deform it. So this structure on the center, you can do a heat treatment, but you can't go and really deform it. Although, I know that sometimes these days when they talk about seamless pipe, and that probably is the best way to go now for a discussion, is there's a specification for a seamless pipe that is very clear that it doesn't mean that you didn't start from a plate and made it into a shape. All it says very clearly is you can't see the welded seam. So let's say that you and I are clever, and we take this pipe and do the seam weld here. So I got it wrong here. We're going to take a big pipe from a plate and we weld it here. So we have our fusion zone. We have a little bit of a reinforcement maybe. Maybe there was a lot of forces, so it formed a lip. When we did resistance welding, we cleaned that off, so it's clean. It still has the welded seam. And then we go through enough drawing operation that all this structure gets broken down back into the equivalent of a hot rolled material. So you have recrystallization, you have diffusion, and in the end of the day, you cannot tell that it was welded before. The same way that if you look at a piece of a bar of steel, you can't tell that it was ever melted because now it has this wrought structure characteristic. So it's a very effective way, and it's used a lot with some very complex extrusion as well. So you do have essentially a fusion process, but it's so far ahead in the process of getting to your final shape that you can't see it anymore. So one thing I want to do is discuss a little bit, plenty of example of class projects. So you're going to do the ski poles, which I think is just perfect, these things. Anything that you like that will push you to learn something. Whatever it is on engineering is great. For last semester, for me, there was one presentation. Somebody studied the San Bruno, California pipeline explosion. There's a report from NTSB explaining, kind of what they found out over the year or 2 years that they were studying, why there were 8 people dying. That's when the NTSB gets involved, when it has a lot of consequences. An entire neighborhood that was essentially burned. And the report spoke to a number of factors. The main one being they didn't really know in details, the pipeline operator, what they had for pipe underground. And when we talk about the consequences of an event like this, it does have a beneficial effect because it did take a while, so it happened in 2010, but this year there is a pending proposed rulemaking that's going to require the operators to go and find out what exactly their assets are, how they welded, what kind of steel strength they have. And a lot of times it's just because the construction standard changed. So these days when they put on new pipelines, they have a lot of extensive requirements they have to meet for material testing, including cracking resistance and all that. But those things didn't even exist. You know, we're talking about the Sharpie. So the Sharpie existed, but the other processes of looking at crack propagation were just not there yet. And just a general expectation in terms of reliability was different. It's not clear that people were thinking these things were going to be in the ground for 40, 50, 60 years. So it's just part of a process of learning from the experience. I think the main lesson learned in that case is it was a very, very long system, and they had a few bad joints, and they just didn't know about it, and therefore it makes sense to go and find out. So we couldn't go right now and dig out all the pipelines that we have in the U.S., where first of all we will freeze this winter. So the only thing you can do is learn from those experiences and then make it better. So just to tie back on the project, is I've given you like probably 5 times what she could do. What she did is, as a presentation, is she focused, okay, this was the incident, and this is what the analysis was, and then she had some images of the joint that she didn't fully understand, and we discussed it in class. So it was great because it did relate to something. In that case, it was a little bit of a welding type situation that was analyzed. And you know, Professor Eager, myself, and Brian, I'm sure, are available if there's any question along the way. Just send us some images. Say, I don't know about this, or I don't know about that. Well, that's what we're here for. You get free consulting. We say that a lot, and not just during the class. If you, I have people now that already started looking for jobs for graduating this coming year, and my advice is, yeah, network. You know, so I know some of you were at the career fair. That's great, but we have the alumni directory that you go and connect, and don't just ask for a job. Just ask for advice. Just ask to connect to people and learn something, so you know more what is most applicable to you. So it's very. I mean, a lot of times I see these things you know, I'll have the students say, well, why don't you send me a draft of what you'd like to send this person? And it just starts like, I'm interested. They don't care what you're interested in. You know, you need to try to explain what, it makes sense if you're contacting someone that you need something from them. So you might as well be clear what you like. So if you like a job, that's great, but I think you also want a network is an important aspect. And if you can put that in a very short paragraph, they know that it won't be having a hard time discussing with you because you're going to be very respectful of their time. Everybody is just so busy. I mean, you guys are busy as students, and it doesn't get any easier. That's all I'll say. So we'll end the day like this. Thank you so much.